Wait, so no, I
Okay.
don't.
Yeah. All set?
No, wait a moment. I can't see the presentation anymore.
Okay.
Do you see the... Wait, I'll stop sharing for a moment. Now I see my presentation again. Okay, yeah.
Okay. So welcome everyone to today's row. It's my great pleasure to introduce today's speaker, Ward Romeijnders. So Ward is an associate professor, full professor now, full professor at the Department of Operation at the University of Groningen in the Netherlands. He's doing research in integer optimization problems under uncertainty, both on the stochastic optimization, but also on robust optimization, with a variety of applications from energy, healthcare, finance, logistics, and so on. He has published very high quality papers in well-known journals like Operation Research, MathPro, SciAm Optimization, just name a few. And also is an associate editor of Mathematical Methods of Operation Research. So it's a pleasure, Ward, to have you here. And without further ado, I want to give the control of the screen
Yeah.
and the mic to you.
Okay, thank you, Reza. So I will talk about multi-stage robust mixed integer programming. So this is joint work with Christoph Postek and Wolfgang Wiesemann. But actually it will be consisting of two parts. So parts of my work with Christoph on two-stage robust mixed integer programming, where we investigated piecewise constant decision rules. And in particular, we found a way how to identify which uncertainty scenarios are crucial if you want to iteratively improve your piecewise constant decision rules. And then the second part of the talk will be about multi-stage robust mixed integer programming, which is joint work with both Christoph and Wolfgang, where we investigate a finite adaptability approximation. And I'll discuss how the algorithm behind this approximation works, and I also show some numerical experiments. So first, two-stage robust mixed integer programming, which is based on our Informed Journal on Computing paper. And so in two-stage robust mixed integer programs, we have to make some decisions, x1 here and now, in the first stage, before some of the parameters, uncertain parameters psi, are known. And then later in the second stage, we can make some decisions x2, which are adjustable. They can be made when we know the realization of these uncertain parameters. So x1 is made in the first stage before we observe psi, and then we decide upon x2 in the second stage. And so the corresponding two-stage mixed integer robust optimization problem is as follows. And we minimize both over the here now decisions x1 and the policy x2, so which determines the second stage decision for every realization of uncertainty psi, given that we minimize a certain worst case cost, where both the first stage cost and the second stage cost can be uncertain. And we also need to make sure that several constraints hold for all possible realizations of the uncertain random parameters in an uncertainty set psi. And so this model is a mixed integer robust optimization problem. And these sets x1 and x2, they impose or may impose integer restrictions on some of the components of x1 and x2. And so also observe here that there is uncertainty in all the parameters of the model, only not in the right-hand side, but this is without loss of generality, because if there is randomness in the right-hand side, you can move that to the uncertainty in the constraint coefficients by adding a dummy variable. And so we make several assumptions. So we assume that the uncertainty set is polyhedral, non-empty and bounded. So it looks something like this. And we also assume that all the parameters are affine in the uncertain parameter psi. Okay, so what are the main challenges of solving this two-stage mixed integer robust optimization problem? Well, for one, it's NP hard. Why? Well, already a deterministic mixed integer linear program is NP hard. So also the two-stage version is NP hard. But even continuous two-stage robust optimization, so continuous adjustable robust optimization is NP hard. And so we're kind of combining the difficulties of both worlds, the two-stage part and the integer part. And also, we cannot use linear decision rules here, which is common in the continuous case. And that's because there may be integer restrictions on the second stage variables. And if you have linear decision rules, it will be really hard to get feasibility of these second stage parameters here. And so in the literature, there are several ways of dealing with decision rules that allow for integer decisions. And the one that we are going to consider here is to use piecewise constant decision rules. And so here, this is just the two-stage mixed integer robust optimization problem that I showed you. What are we going to do? Well, we're going to partition the uncertainty set into several subsets. And so, for example, like this. And then we're going to assume that for every uncertainty in, for example, this first subset, we have to pick the same decision. And so our second stage decision needs to be constant over this set. It also has to be constant over the second set, but there we can pick a different decision. And so essentially, we need to implement a constant decision, constant second stage decision x to s, if nature picks an uncertainty in subset psi s. And so here, the decision rule is we select x to psi as one of several options, depending on in which uncertainty set nature picks its uncertain element. It's good to mention that we are allowed to decide upon these decisions that we make later up from now. And so throughout this talk, I'm going to assume that all these partition sets, that they are polytopes, so that they are separated by hyperplanes. And so under this assumption that we're going to use a piecewise constant decision rule, the optimization problem that we get, which is a static robust optimization problem, is to minimize over the here and now decisions x1. But also, here and now, we determine what is our best response if nature picks an uncertainty from the first partition set. That's x to 1. And we determine that decision for each of those uncertainty sets psi s. And so x1 should be feasible, also satisfy possibly some integer restrictions, and also all these decisions, second stage decisions, need to be feasible. And it also means that for every psi in the uncertainty set psi s, we need to make sure that the decision, first stage decision x1 and second stage decision s that we make within this uncertainty set, that they combined are feasible. And so the objective is still to minimize the worst case expected cost, where nature can pick any uncertainty, and essentially that's equivalent to first selecting from which set S, and we pick the uncertainty and then pick the worst over that set. And so given that nature picks an uncertainty from the set psi s, these are the corresponding worst case costs, and nature can pick the worst case partition over here. Okay, so I want to compare the two models with each other. So the original two-stage problem and the one that we obtain using our piecewise constant decision rule. And I've rewritten them here slightly, so I've put them in epigraph form, which means I've introduced a new one-dimensional decision variable theta, and I'm just going to make sure that theta is equal to this worst case cost. So the maximum of Q1 psi transpose X1 plus the second stage. And so if you move this to the other side, you see that theta for every value of the uncertain parameter is bigger than the cost. So it really is the worst case cost. And also here I do the same. So I added this theta variable, but I now make sure that for every partition subset and for every scenario within the subset, theta is bigger than the corresponding cost. So this is also the worst case cost. Okay, so first observation, solving this model, the optimal objective value gives us an upper bound on this adjustable problem, on the true two-stage problem. Why? Well, we're minimizing, and in this problem, we have restricted our possibilities for the second stage decision. We have restricted the options that we have because we enforce that our decision has to be the same for many scenarios in a certain partition set, while actually here we are free to select any x2 for every uncertainty. Yeah, so if we have restrict our decisions, we're minimizing, so the objective value is an upper bound. The advantages, however, of using this piecewise constant decision rule is that we now have a static problem. And we only make here and now decisions. And there are no second stage decisions anymore, because already in the first stage, we are determining what we're going to do in the second stage. And so in fact, the robust counterpart of this problem that we get when we deal with these infinitely many constraints by duality, the robust counterpart is just a deterministic mixed interlinear program. And we can solve it, for example, with branch and bound. That's in contrast to this two-stage problem, which is more harder to solve in general. And what's also nice about this problem here on the left is that we can refine the partition and in that way improve or possibly improve the upper bound. For example, if we partition or refine the partition like this, we now are not restricted to one decision within this set anymore, but actually we can now pick a different decision over here compared to over there, which gives us more flexibility, which may reduce the upper bound. In fact, in literature, it has been shown that under mild conditions, if you keep refining your partition and make sure that all these subsets are getting smaller and smaller, as long as they are small enough, then the optimal objective value of this problem converges to the true optimal objective value of this adjustable problem. Okay, but this is in the limit, right? I mean, in a practical algorithm, when we need to solve it using a computer, we cannot keep on refining these uncertainty sets indefinitely. So main research questions in this project are, how do we iteratively partition this uncertainty set? And can we also come up with optimality conditions that make sure that we do not need to partition any further, but that our upper bound is tight, and that we actually already found the optimal solution over here. And hopefully we can do that without making all of these partition sets arbitrarily small. And so for the continuous case, this problem already has been solved. For example, in this paper by Christoph and Dick. And I want to show you how this works first before I can go on to the integer setting. And so first I want to focus on how can you do this partitioning in the continuous setting, and meaning that all decision variables are continuous. And so here I also remove these integrality constraints. I'm now assume that we are in the continuous setting, there are only continuous decision variables. And then here the first observation that I want to make is that in this problem, there is no uncertainty in the cost and also not in the right-hand side. And so this is a continuous static robust optimization problem with uncertainty only in the constraint coefficients. And so in some sense, it's a special case of this, what I call generic static continuous robust optimization problem, where we have some continuous decisions X, deterministic linear cost. We have linear constraints where the right-hand side is fixed, but the constraint coefficients, they're uncertain. And for each constraint, they can belong to a different uncertainty set. And so in here, in this problem, sometimes they are the same, sometimes they are different, depending on which subset S we're considering. But in essence, it's just a special case of this problem. Yes, we can rewrite this problem using a duality result from Beck and Mental, which is known as like primal worst equals dual best. And so here, this LP, it's a primal problem where we need to deal with the worst case. So we need to consider all AI in the uncertainty set. And if you construct the corresponding dual LP, we have our standard dual variables Y. So the objective is B transpose Y. We have the standard constraints, but now we're allowed to pick the best possible constraint coefficients AI per uncertainty set. And so the best case, the dual is maximizing, so we can pick the ones that makes this dual as high as possible. And so, of course, I assume for the moment that we can solve the dual problem. Then I want to call Y bar and A bar the dual maximizers, so the maximizers of this problem. And I define an index set I bar as all indices for which IY bar is bigger than 0. And then I call all corresponding A values, A bar values, critical scenarios. So why is that? Well, if you look at this dual problem, if yi is 0, it's not contributing anything to the objective function, also not to the constraints. And so I can leave all of those out. And then if I also insert the optimal values of AI over here, I know that this problem is equivalent to this one. But this is now just a LP in terms of the yi variables that we have left. So by standard LP duality, I can change this into a primal problem again, where we still have decisions X, deterministic linear costs, but now only the constraints corresponding to the critical scenarios. And now you can also see why we call them critical scenarios, because via this dual path, I know that this original robust optimization problem, which has infinitely many constraints, has the same optimal objective value as this problem, which only has finitely many constraints. So the critical scenarios correspond to the, let's say, critical primal constraints that as long as they are there, we can remove all the other constraints, but we keep the same objective value. And so some of the observations that I want to make here are that for every constraint I, there is at most one critical scenario. There may be 0. If yi equals 0, then it's not a critical scenario. And otherwise, this maximizer, that is the critical scenario. Also, by complementary slackness, we know that the optimal solutions to the yi variables that are left over here, they're greater than 0, strictly greater than 0, which means that by complementary selectness in the optimal solution over here, all these primal critical constraints actually need to be binding. So they actually need to hold with equality over here. And also, as I've already said, these critical scenarios identify a kind of critical set of primal constraints. Okay, so what does it mean for our partition problem, which we said was a special case of this generic continuous static robust optimization problem? Well, for every constraint, there may be a critical scenario. And I call the critical scenarios corresponding to these constraints psi bar 0, s, and these psi bar I, s. And we also know that there is at most one per constraint. So here I've listed all of them, but some of them may not be critical at all. But there is for sure at most one per constraint. And so what I can do, I can group them per subset. So here you can see that I can focus on all the scenarios corresponding to a single subset S. And there may be some over here and there may be some over there. But all of them, I group them in a set which I call X bar S. So if this is the partition set, maybe for this first set, I find a critical scenario corresponding to this original constraint, and maybe that's the only one. Well, for the final one, I actually find 3 critical scenarios. Yeah, so how does this help us? Well, it turns out that the optimality criterion is that if for all these sets, if they all contain at most one element, then the upper bound is actually tight and the optimal objective value corresponding to this problem is equal to that of the true optimal objective problem. Okay, so why is that true? So let me give you an interpretation of why this result holds. Suppose for the moment that for simplicity that for every subset, there is exactly one critical scenario. So just for every subset, there is exactly one. Then we know that this problem over here is the same as the one in which we replace for all constraints just the corresponding critical scenario. Via the dual route that we saw before, this should give us equal optimal objective value. And so maybe I added too many of the scenarios, but if I had more constraints out of these, then this should still be correct. The optimal objective value should still be the same. So if we look at this problem over here, then I claim that this is actually a two-stage problem, but one corresponding to an uncertainty set in which there are only finitely many scenarios, namely the critical scenarios. Why? Well, we can make the first stage decision x1 here and now. And then x2s is just a response that we make when we observe psi bar s. And there is just one scenario left per subset. So this is in some sense just a two-stage problem with a finite uncertainty set. And so it means that the objective value of this partition problem is equal to this two-stage adjustable robust optimization problem with a relatively small scenario subset. And when you think about it, if the subset becomes larger, so in our original problem, it means that nature gets more power, which means that the original problem should have an at least as large objective value. And so this means that our objective value is a lower bound for the true adjust on robust optimization problem? Well, originally we also said it was an upper bound. So now it's both a lower bound and an upper bound, so they should be the same. Okay, so that's very useful because it means that sometimes we can stop our algorithm even when we have still quite a large subset over here. Just if there is everywhere only one single critical scenario left, then we can stop. If not, then we can improve the partitioning by making sure that we split the critical scenarios per subset. And so, for example, for this problem over here, we may improve our upper bound if we make sure that we split this subset in such a way that some of the critical scenarios go into one of the subset and the others in the other one. So with this example over here, this will for sure not improve the upper bound because all the scenarios stay in the same subset. Essentially, why can't we improve? Well, because all the critical scenarios that are there in this problem will be there in the updated problem as well. Why? Well, if we do this partition, then all the constraints remain the same for the original subsets. And so that stays the same. But for this new one over here, there the uncertainty set becomes slightly smaller. Yeah, but all the critical constraints are still in there. So all these critical constraints are still in there, and there may be some extra constraints due to the new partition set, but they just add extra constraints. Even though with an extra variable, they're just extra constraints, which means we cannot go down any further because all the critical scenarios are still there. Well, if you split the critical scenarios, then now you're allowed to make a different decision for one of the critical scenarios compared to the other ones, which means that this critical set of primal constraint is destroyed, and now there's a possibility that the upper bound may improve. Okay, so let me try to show you this mechanism on a very small problem in which we have a two-stage continuous adjustable problem with two adjustable variables. So only second stage decisions, no first stage decisions. And for simplicity, there are only two scenarios in the uncertainty set. Then here, this is the feasible region for the second stage variables under the first scenario. And so I'm assuming we're minimizing in this direction. So this is currently the best decision that we can take. But if nature picks the second scenario, then this is the feasible region for the second stage decision, and this is the optimal solution. And so this is a better solution than that one. So what nature will do in the two-stage problem is to select the first scenario, this one, and then we select the best decision, x2 star, xi1, and we end up over here. If we would have decided to first solve this problem with a piecewise constant decision rule, without partitioning the uncertainty set, we would have to make the same decision for both xi1 and xi2 for both scenarios. So we need to be feasible with respect to both scenarios. Then this would have been the optimal solution over here. And if you look at the solution, you see that there are two constraints binding over here, and they both correspond to the first scenario. So the critical scenario in this problem is really the first one. There is only one critical scenario, so it means we do not have to do any partitioning. This is the optimal solution. And it makes sense because it is right. I mean, it is equal to the optimal solution that we found when we looked at the two-stage problem. Okay, so I hope that the partitioning idea is clear in the continuous setting, because now I want to try to explain what happens if we add integer decisions. And so suppose for the moment that the second stage variables are integer, and so they need to be one of these points over here. If we then use a piecewise constant decision rule, the best integer decision is over here. But there are no constraints binding over here. So it's unclear if there is a scenario critical, yes, no. For the LP relaxation, only Xi1 is critical. And actually, if you look at the constraints, then the one corresponding to Xi1 are closer than the ones corresponding to Xi2. So it seems here that, yeah, Xi1 may be the only critical scenario. But it turns out that in this problem, partitioning does help. And to see that, suppose we only, when we see only Xi1, then we can pick this decision over here, which is better than this one. And in the second scenario, we can pick this decision over there, which is also better than that one. And so in fact, both of them are better than the one that we get from the piecewise constant decision rule. So partitioning definitely helps over here. Probably this is the best. So then nature will pick the first scenario and we will pick this decision in the two-stage problem. And so going back to the integer setting, and so now the integers are back, it's really the question, what are the critical scenarios? And can we derive an optimality criterion similar as before? And in some sense, this was the starting point of our research project. Can we do something similar when integer decisions are involved? And the answer that we found was that we can find those critical scenarios and we can actually extract them from the branch and bound tree that is used for solving this partitioned robust optimization problem. And so remember, the robust counterpart is just a mixed integer linear program. If you solve it by branch and bound, then I claim that from the branch and bound tree, we can extract the critical scenarios. And so let me explain what I mean. So here's just an example of a branch and bound tree where we have branched on some of the integer decision variables, either in the first or in the second stage at each iteration. And in each node of this branch and bound tree, we solve its continuous or LP relaxation. So there are no integer constraints in this node. We do have all the original robust constraints, and I added these constraints, which are branching constraints. It's just a general form of saying that first component of x1 is either smaller than 1 or bigger than 2, or for some x2s, first component is smaller than 0 or bigger than 1. There are some branching constraints at this node. Okay, but that means that at each of these nodes of the branch and bound tree, I'm solving a continuous static robust optimization problem. Which means that for each node, there may be critical constraints corresponding to that problem. They may be different per node, because there are different constraints in every node. But in some sense, every node will give me a set of critical scenarios, telling me which of the primal constraints here are critical. And so what do? We take the union over all those critical scenarios. Not of all of them, actually. We show that we can restrict ourselves to nodes in a certain critical cut set that satisfies the following criteria. The objective value of the LP relaxation in the node is bigger than the optimal objective value of the integer problem. Not in a node, the total optimal objective value of the integer problem. And also the node should be, the collection of nodes should be such that it cuts somehow a path, all the paths from the root node through all the leaf nodes of the branch and bound tree. And so for example, in this first node, the root node, the LP relaxation is probably pretty good, pretty low. So it's lower than the optimal integer objective value. But maybe after branching, we find an optimal integer solution over here. So the LP relaxation is equal, but at this part of the branch, the LP relaxation is still smaller until at some point LP relaxation becomes bigger and bigger because we add more branching constraints. And now I'm focusing on these nodes. Because here the LP relaxation for each of them is bigger than the optimal integer objective value, and it cuts the entire branch and bound tree. And now we can show that if, again, for every subset, this set of critical scenarios, there's only at most one critical scenario, then the upper bound is tight and we found the optimal solution. We do not need to partition any further. And the idea is as follows. Again, if there is only one critical scenario among all those nodes for S, then in this node of this branch and bound tree, we can again replace all the constraints, but only the critical ones. And then this nodal problem is actually also a nodal problem of the two-stage robust optimization problem with a finite number of scenarios, namely only the critical ones. And what do I mean here? Well, suppose we have this adjustable robust optimization problem, then we have the same decisions as over here. And I don't know if it's optimal, but what we could do for sure is we could make exactly the same branch and bound tree for this problem. And so do exactly the same branching on the same constraint, the same integer constraints as we did in this problem over here. And then in every node of this problem, the critical constraints are still intact. And so the LP relaxation that we get at each node is for sure bigger than theta bar n, so also bigger than this integer robust optimization optimal objective value. Which means that if you look at the total objective value of this adjustable robust optimization problem, it will be one of the integer solutions in one of the LPs corresponding to this node, or that node. But the best LP relaxations in all these nodes is not better than this arrow S value, which really means that this is a lower bound, arrow S is a lower bound on our problem, and for the true optimal objective value, it might even be bigger. Similarly, now we have a lower bound for a problem, while it's also an upper bound, so it's equal over here. And so by looking at these scenarios in the branch and bound tree, if it's just one for all subsets, then we can stop. Otherwise, we need to split them, and that's how we improve. And that was the main contribution of this this first two-stage part. Okay, then I also want to say something about the multi-stage work that I've done with both Christoph and Wolfram. So this was not a two-stage setting, but really a multi-stage setting with a longer time horizon, where we're dealing with both state and control variables. Also uncertain parameters at each time stage, and I denote the history by xi t, so that's xi1 until xi t. And so first we decide upon x1, y1 in the first stage. Then we have the uncertain realization, xi2, before we pick the values in the second stage, etc. And so the multi-stage formulation is as follows. We minimize the policies for the state and the control variables. The state variables might be integer, but the control variables are continuous. We minimize the worst case cost over some uncertainty sets xi. And for each stage t, the stage t parameters only depend on xi t and the previous state variables from the previous time period. Okay, so typical challenges with this problem is that, again, linear decision rules do not work because we're dealing with integer state variables. But also the partitioning approach that I showed you for the two-stage setting becomes computationally expensive when you move to multi-stage settings, in particular if this time horizon becomes longer. So what we propose to do in this setting is to use a finite adaptability approximation, which means that we are going to restrict the number of state variables by a small predetermined number of candidate values. And so these are predetermined. They are not optimized within the algorithm. They are input to this minimization problem. Yeah, so the only thing that changes here is that in every time period t, we can now only select from a limited number of candidate decisions. And so if you compare that with the partitioning approach, well, first, when we partitioned, then the partitioning was predetermined, and we needed to pick the best decisions for each partition set. In the finite adaptability, there's no partitioning. The decisions are predetermined. But then for every psi, we need to figure out which decision is best. And so there's a kind of implicit partitioning. Because there will be parts of the uncertainty set where one decision is better and parts of the uncertainty where the other one is better. So the methods are not the same, but there is a relation between the two. Okay, so before I explain how we solve this finite adaptability approximation, I first want to say something about the uncertainty set. And so in each stage of the problem, we assume that the uncertainty consists of what we call interstage uncertainty, which do not only impact current stage t, but also the possible uncertainties in later time stages. And there is intrastage uncertainty, which is only relevant for stage t. And so we assume that this interstage uncertainty depends on the previous stage, and that there are only finitely many options for those. And while the interstage uncertainty can be a polyhedral set like before. And so this contains special cases, stage-wise rectangularity, where we essentially do not use any interstage variables, but the uncertainty sets are kind of independent of each other. It contains discrete lattice regimes where the interstage uncertainty can be modeled by a lattice, in which you can move from time stage from one to the other through a lattice. But even some kind of Markovian regime, where in each stage t, you have the same finite states of options for your interstage uncertainty, and which ones you can move to can be independent of the time period in which you are in. Okay, so to solve this finite adaptability approximation, we look at its corresponding nested formulation, where we define for every stage t the worst case cost to go function. And so this worst case cost to go only depends on the previous state variable and the previous interstage uncertainty. It's a maximization over psi t, and then we minimize over the state variable and the control variable, where the state should be one of the pre-selected candidates. And of course, we also need to deal with the worst case cost to go of all the remaining stages. And what's important to mention here is that there are only finitely many options of these, and only a number of pre-selected candidates for the state decisions. And so there are not too many options, values that this worst case cost to go function can take. And that's why we can also interpret this problem now as just a two-stage mixed integer robust optimization problem, which we can iteratively solve. For example, suppose we would know all the worst case cost to go functions for the remaining time periods, and then to know the worst case cost to go function at time stage t, we just need to solve this two-stage mixed integer robust optimization problem. And that's also what we propose to do. And so via backward recursion, we start at the end of the period, and then we solve these worst case cost to go functions going back through the time stages. And so the advantages of doing so is that the problem decomposes into many smaller two-stage problems. In fact, this is the number of problems that we need to solve. Many of these problems can be computed in parallel because all the problems per time stages can be solved separately, so it's in parallel. The framework is pretty general because we can solve this exact, but we could also use a conservative approximation. And then we do not get a conservative, an exact solution method, but a conservative approximation of the total multi-stage problem as well. And what it also does, it exploits the low cardinality of this candidate number of decisions. So it actually does that in two ways. First, there are a limited number of states, so we do not have to solve that many worst case cost to go functions. But also in many situations, we can exploit when we solve this worst case cost to go function, that there are only a low number of candidate decisions here. In fact, in the paper, I'll not go through it here. We can come up with LP or MLP formulations of this problem because this cardinality of the candidate decisions is small. And so here are some of the cases in which we can do that. Of course, we can also use conservative approximations, which includes the piecewise constant decision rules that I've mentioned before. In this case, only on the state variables. This can be an exact approach, but it can also be an approximation if you stop partitioning at a certain point when you haven't reached optimality yet. Okay, so I'll skip for time being how we do that. But I want to mention that, of course, I haven't discussed how to select these candidate decisions. Because that's a difficulty that we may face. And so for that, we have a heuristic approach where we first initialize the set of candidate decisions. We solve the finite adaptability approximation via the backward recursion that I just mentioned. And then we use the solution that we get to identify worst case uncertainties. The uncertainties that were the worst. And then we again solve this finite adaptability approximation, but now with all possible decisions X, all possible state decisions, with a much smaller set of uncertainties. And the idea is that if we now find some decisions that are optimal that were not in our set of candidate decisions, we can add them and then we can repeat this loop until at some point we do not update this set of candidate decisions anymore and we stop. And so this is heuristic, but it may be effective in particular if you have to deal with multi-stage problems with a very long horizon. Also, I want to mention that we get a upper bound in the second step and a lower bound in the third step, so that during the algorithm we can see how close the lower and upper bound are. Okay, so we tested this problem on two applications. The first is a route planning problem, where we have a graph with 100 nodes and approximately 600 arcs, and we need to find the shortest path from the left corner to the upper right corner. And this red arc specifies the optimal solution if there is no uncertainty in the problem. We, however, assume that nature has a budget, fixed budget over time, to increase the arc length in different time stages, and that we dynamically can choose which path to take. So in the first stage, we determine what our next node is going to be. Then we observe which arcs nature is going to perturb, so increase the length. We pick a path, and then nature can go again, etc. And so we were able to solve this problem exactly with our method. So not using any heuristic, so really get the accept optimal solution. And we compared it with the static robust route, where we first need to pick the route, and then nature can decide which arcs in which time periods to increase. And the worst case perfect information route, which means that then nature first needs to determine where to perturb the arcs in the worst case possible, and then we can use that information to take our best route, to make our best route. And so here you see the length for different values of the budget, the static robust route, our dynamic method, and the perfect information or crystal ball method. And you see that there's quite a difference in the length between the static and the dynamic route. So making dynamic decisions really pays off in these type of problems over here. And so we also investigated how these routes look like. So here, when there is no budget for nature, then the dynamic and static route are just the same, the one you've seen before. But here, if the budget increases, then there is just a single static route. While we also investigated what happens if we just simulate where nature increases the arcs, and then still make decisions based on the worst case policy that we have obtained. And there you see that the dynamic route really takes different paths, and it really uses the information at each time period that it gets from nature. So what decision it has made to go more effectively or quickly through the network. And so finally, we also considered a location transportation problem with a time horizon of t is 10. So in this problem, we had to determine where to build facilities, possibly iteratively over time, to serve customers that are there with uncertain demand. And we did this with, for instances, up to 20 facilities and 40 customers. And so I won't go into too much detail about the problem, but we heuristically selected the candidate decisions, like in the method that I showed you. And we compared with 3 approaches. Our approach, assuming that the interstage was only nominal, so completely assuming nominal interstates away, and also assuming in one method that the state variables can only adapt or cannot adapt to the interstates variables, which also simplifies the method considerably. And then in these graphs, you can see how the lower bounds and upper bounds look for the 3 different methods. And in particular, if you look at the lower bound, you can see that only our method is able to come up with good lower bounds. Here, the green and the red lines are not even on the figures. And our method is also faster than, for example, the nominal interstage model. And it's really because we work with only a small set of candidate decisions. Well, in this nominal problem, still every time all the possible candidate decisions are considered, and this makes the problem much slower. Okay, so that's all I wanted to tell you. So thank you for your attention.